So first of all, I want to say something about the survey that we put on Slack. So thanks for those of you who filled it in. I guess I'm probably moving a little faster, so I'll try to slow down a little. But regarding the quite a few of you said that there were too few proofs. So I guess somehow I didn't mention in the beginning of the lecture that I would like to, in the end, introduce the root datum for connected reductive group. So these are combinatorial data that classifies connected reductive groups and also compact connected Lie groups. So to get there, I need a lot of preparation, and this subject also the proofs is for many of the proofs is quite complicated, so it's difficult to cover many proofs. So unfortunately, moving forward, there might be even less proofs, but hopefully the good side is that we have all these books that we can try to go fill in the details. And also, I guess the idea is to get you guys interested in algebra groups. If you are indeed interested, then you can go look into the details of the proofs. Okay, so today we wanted to first discuss commutative algebra groups. So these are just linear algebra groups which are commutative as abstract abelian group. So now G is a commutative linear algebra group. So as always, so G will be a linear algebra group. So I just say that G is commutative. So then last time we introduced Jordan decomposition in the group. So now we write GS to be the set of all semi-simple elements in G. And then we write GU to be a unipotent elements in G. So now if the group G is commutative, then maybe in the exercise you already proved that GU is a closed subgroup. So then in this situation of a commutative group G, then these both sets actually are closed subgroups. So moreover, so using the Jordan decomposition again, so first of all, we can see that there is a natural morphism from GS cross GU to G, and then again, because G is commutative, this is actually an isomorphism of algebra groups. So now I'll just provide a maybe two-line idea of the proof. So what do we think? Why is the GS and the GU closed subgroups? So maybe we can just consider G as a subgroup of G of N, right? Using our main theorem from first day. And then now, last time we also said, now you can think of G as a set of commuting matrices, right? So then what can we do to them? So they should be able to be simultaneously upper triangular. So we can assume that the G is in the subgroup of upper triangular matrices. Then now, if we look at in the upper triangular matrices, what are the semi-simple elements and what are the unipotent elements, then we know that GS is going to be G intersect with the diagonal matrices, right? Those are the only. No, sorry, that's not true. But we are using the fact that the GS is simultaneously diagonalizable. So we can put the GS in Dn. This is diagonal. And then GU, you have proved that it's closed. So, okay. So then for the second part, so as, first of all, you see that this is isomorphism of abstract groups, right? Because of the Jordan decomposition again, and the G is commutative. So this is a group homomorphism. So pi is just, if you have GS, GU, you maps to GS times GU. And then now you can also have a inverse morphism from G to GS cross GU by G goes to GS inverse G. So taking the semi-simple part of G, we know that this is unique, and so the rest we will I'll not discuss the details. But so see, this theorem now tells us to study the commutative algebra groups, so we can just look at the either groups consist of only semi-simple elements or commutative unipotent groups, right? So now let's first look at the those groups that's commutative and also consists of semi-simple elements. So these are the so-called diagonalizable groups, and then there are some special ones are torus. So let's begin with some definition. So if you again have a algebraic group G, you can consider homomorphisms from G to GM. So now, because of this special G goes to GM, we give it a special name. This is called a rational character of G. So all just a character of G. So we will denote the set of character of G by X up star G. And then similarly, you have a homomorphism lambda from GM to G is going to be called a co-character. And then we will write X lower star G for its set of co-characters. Well, this is some special homomorphisms. Now let's look at the so-called diagonalizable groups. So I guess it's kind of already intuitive, so diagonalizable. But the formal definition is that it's diagonalizable if, first of all, G is commutative. And it consists of semi-simple elements. So what would be a diagonalizable group that we can think of?
Diagonal matrices.
GM. DN, very good. So so it turns out that so this condition is isomorphic, sorry, equivalent to the condition that the G is isomorphic to a closed subgroup of Dn, which is isomorphic to a product of n copies of Gm. Can you think of a disconnected diagonalizable group. Now, if this group is actually isomorphic to Dn, then we call it a torus. Well, it's an algebraic torus, but nowadays we just use the shorthand. Just call it a torus. Okay, so now maybe first look at an example for these characters and the co-characters. So if I have a G is just the diagonal matrices, so what do we think the homomorphisms to, what are its characters? Trace is not a group homomorphism, right? Raising to some power for the whole diagonal matrix. Okay, very good. That is a character. Are there other characters?
Raising each entry to a different power.
Very good. Raising each entry to a different power. So I guess in your exercise, you showed that for GM, the GM to GM is raising to a power, right? So, okay, so M1 to Mn, and these MIs are, what kind of numbers are they? Integers, right? Okay, so this group, this X star Dn has a natural group structure. So this as a group is isomorphic to just the product of n times. And what about the co-characters? What can I do to map GM to Dn? If I have a number, I wanted to map it to a diagonal matrix. Huh? Multiple of identity, that is okay, but we probably want a little more, right? So what if I tell you that this is also isomorphic to Z to the N? So then what should we put? Is it similar to what we just did? Different powers. Very good. Okay, so now we write down some equivalence conditions for a group to be diagonalizable. So the following are equivalence. So first of all, G is diagonalizable. And what do we think, what kind of group X star G should be?
Abelian.
Maybe I should also ask students in Hawaii if they want.
Free abelian.
A what?
Hawaii is saying free abelian.
Free abelian group. Do we agree with that statement? For Dn, it is, right? So this is a free abelian group. But I asked earlier if you have an example of a disconnected diagonalizable group. Have we Finitely generated, very good. And what kind of group it is? It's a abelian group, right? By definition, so the group structure is just chi1, chi2 G is equal to chi1 G, chi2 G. So because it's landed in GM, so it's a abelian group. And moreover, the elements of X upper star G will form a basis of our coordinate ring KG. Now, something that's also will be useful for us is that any rational representation of G is going to be always a direct sum of one-dimensional representations. So I will not give the full proof again, but maybe we look at why A implies B. So by definition, so G is isomorphic to a subgroup of Dn. So we can just assume that we take a subgroup and look what happens, okay? So then if you have this, this will induce a surjection on the coordinate ring, right? So now, what is the coordinate ring of Dn? Very good. T inverse, but n of them, T1 inverse, and so on. Tn inverse. So so we see that so we also have a map from that takes characters of Dn to characters of G, which is just any character takes to its restriction to G. Of course, it's still a character. So now, because of this surjection here and the structure of KDN, then we know that the image of phi, because each of the Ti inverse is a character, right? So this image of phi will span the coordinate ring, okay? So now we will use a lemma of Dedekind's. So it says that for any group actually, so these characters are linearly independent. So I'll leave this proof of this lemma to be an exercise. But then from this lemma, we see that this map actually is a surjective map. So together, this shows that the elements of X star G will be a K basis, right? So it spans Kg, and it's also linearly independent. And now, what about, is it clear why any rational representation of G is gonna be a direct sum of one-dimensional representations if G is diagonalizable? Okay, so very good. Some of you are nodding. So, so the idea again, you can simultaneously diagonalize them, right? So then your vector space is going to be direct sum of eigenspaces, and all that shows that any representation of G is a direct sum of one-dimensional representations. Okay, so now what are exactly these finitely generated abelian groups that corresponds to a diagonalizable groups? What do we think? Maybe let's first write down corollary of this theorem. So the group X star G has no P torsion if the characteristic of K is equal to P, a prime characteristic or positive. Oh, what's P torsion? Just means that the no element to the power P is, well, depends on how you think of, maybe we think of an additive group, then it means that the no elements has order P. Or P doesn't divide the order of. Okay, so no. Okay, so let's see. So maybe we say this from the proof. So let's assume that I have an element K in X star G, which has a order P. Now I'm writing it multiplicatively. So then this means in characters P, meaning what? So right, if we are in characters P. So then this means Kg is equal to 1 for any G. Right, so there are no such elements. So now in your exercise, you were asked to see finitely generated abelian group without P torsion. Well, here then in characters 0, then there is no, this just means that a free. So the group of characters arising from diagonalizable groups are exactly a finally generated abelian group without P torsion. So what are the actually finitely generated abelian group? What do they look like?
What happens with these two? Because when you're raising to the P power, these two and that negative one start becoming positive
Yes,
So I think we're relying on P being 1.
but that doesn't matter, right? Even if this is plus, then there's still x chi g is 1. Even it's 2.
I'm just wondering, are you using freshman string step? Is that the step there?
Hmm?
Are you using freshman string here?
I don't know what's freshman stream.
X plus y also power p is x to the p.
Yes, yes,
Yeah.
yes. So if you want in characters 2, I can write the chi g plus 1 to the 2 equals to 0. So then this means chi g is equal to 1.
Right. Okay.
Okay, so what are the finally generated abelian groups? So you can have Z mod NZ, right? And you can also have Z to the powers. So now what would be, so without P torsion, meaning P does not divide P, or NP is equal to 1. Okay, and then what would be a diagonalizable group correspond to this group? What about the group mu n, which is the nth roots of unity? So every diagonalizable group is going to be a product of Z to the n, and with then product some finite groups Z mod NZ, so that P doesn't divide n. Okay. So now we wanted to discuss a proposition called rigidity of diagonalizable groups. So if you have G and H are both diagonalizable, and assume you have a connected affine variety. So, and you are given a homomorphism X to G times G to H cross G to H, so that this morphism satisfy the following condition. So for any X in X, the map induced from this mapping G to phi of XG is a homomorphism from G to H. Then this homomorphism actually is independent of the choice of X.
Do you want X to be connected or reduced? Because if it's not upright.
Yes, I think I do want it to be connected. Yeah. I mean, it works for connected. I hope. Let's maybe we take a look at a brief proof of this. So, I guess I forgot to repeat the question. Question is if I wanted the X to be connected or irreducible. So the idea of the proof is that you take any character of H. Now you look at the value of this character on phi xg, and then this is gonna be equal to So you can write this in terms of characters of G. Oh, sorry. What? 5 star is as before, so it's the map induced on the affine coordinate ring. So now the idea is that the left-hand side is a character. So now using our independence of characters, so you can conclude that there is only one f chi c, so that this is 1 and 0 for the others. So this implies that for everything, for all the chi's, this f will satisfy this condition. But now because x is connected, so this tells you that the whole function has to be 1 for one chi and 0 for the other. Sorry. I'll let you again think through this proof maybe during a problem session, and also convince ourselves that it actually connectedness is enough. So now corollary. So this corollary is important for us later on. So if now H is contained in G is diagonalizable, G, no constraint on G. So then the normalizer group of H in G has the same connected component, identity component as the centralizer. And from here, you deduce that the NGH mod ZG is finite. So for those of you who have seen vowel groups, so later on, this will be, when H is a torus, this will be the vowel group that's important for us. So this proof is follows from the rigidity theorem. So you can apply that theorem to the following map homomorphism. So GH maps to GHG inverse. So now I'll let you apply the rigidity theorem. Seems like I'm still going too fast. So now some comment in the case of a torus. So usually we will write, well, sometimes we write x to be x upper star t. Y is x lower star t, the co-characters. So now these two somehow are due to each other, right? So if I take an element in x lower star t, then I get a homomorphism from Gm to T. And if I take an element in x upper star t, I get a character So now if I compose these two maps, then I will get, what can I produce from this map? From the composition? What can we see about? An integer, right? It's a map from GM to GM, so I get an integer. So we wanted to denote that integer to be a pairing of chi and lambda. So chi lambda is in Z. So a little lemma is that this pairing define a perfect pairing. Between X and Y.
Can you define a perfect pairing?
Hmm?
Can you define a perfect pairing?
Say that again?
What does it mean to be a perfect pairing?
Oh, yes, I will say that.
Oh, sorry.
Yeah. Oh, the question is, what's the definition of perfect pairing? So means any homomorphism from X to Z is of the form chi maps to the pair. Oh, sorry. You can see, I can see it on my, thanks. Oops. Chi lambda for some lambda in Y. So similarly for Y. So later on, we will use this pairing for the root data. So these are, now we have dealt with the commutative groups consisting of semi-simple elements. So I think I will skip the discussion of elementary unipotent groups. So these are not somehow so easy to discuss in characteristic, but I'll refer you to the book of Springer. So basically, in characteristic 0, all the elementary unipotent groups are GA product M times, and in characteristic P, you can allow things like Z mod PZ. So these are the so-called elementary unipotent groups. So I'll mention this theorem again without proving it. So if G is now a connected linear algebra group of dimension 1, so then G is actually either GM or GA. So somehow kind of idea is that, so if G is connected of dimension 1, you can show that the G is commutative. And then by our earlier discussion of commutative groups, you know that the G is either GS or GU. So then you use the discussion about elementary unipotent groups and the diagonalizable groups to deduce that that the G is either GM or G. But in characteristic P, even this theorem is quite non-trivial. So so I won't be as I said, if you are interested, please look at the book. And there are several different proofs too. So Okay, so next I wanted to discuss connected solvable groups. So it turns out to study the structure of our algebra groups is these connected solvable groups plays an important role. So let me start with a theorem called the Borel's fixed point theorem. So solvable here is just as you in your abstract group theory solvable. So a connected solvable algebra group, linear algebra group, G acting on a non-empty projective variety. So if you know what the complete variety is or proper, so you can replace projective by complete. So has a fixed point. So again, I'll write down some idea of this proof of maybe it's a proof due to Steinberg. So we wanted to use induction on dimension of G. So if dimension G is 0, then of course the G is just consists of one element, so there is nothing to prove. Now, assume the dimension is positive, then we can look. So we want to use the property of the group being solvable. So how do we try to where should we use induction from? Which group do we want to have as a smaller dimension group so that you can use induction?
The commutator subgroup.
Do we all recall what the solvable means? Commutator subgroup, where it is. So let's write DG to be the commutator subgroup. So this is a closed subgroup in G, but it's not equal to G because G is solvable. So this dimension is less than dimension G. Then we can use induction. To deduce that this derived group DG has a fixed point or commutator subgroup. So now, if we take the set of all fixed points under this group DG, then exercise is to show that this is a closed subset in the original projective variety. So now W is also projective. So this means that we can assume, so DG just acts trivially on our way by replacing V by W. Okay, thanks. So now we use what we discussed in the first day. So the action of G on this projective variety has a closed orbit. So this tells us that the quotient has a morphism to G dot V. So the orbit of V. So now, now because DG is contained in the commutative subgroup is inside GV, so this tells us GV is a normal subgroup of G. So now then we know from our discussion of quotients, this now is an affine variety, and it's actually affine algebra group. And now this right-hand side is a projective, and this map is actually bijective. So I use some algebra geometry fact. So again, we can just take it for granted for now. So tells you that now G mod GV has to be just a point. So this tells us G is equal to GV. So we have proved that V is a fixed point under G, right? Okay.
Sorry, what factor you use?
Sorry?
What factor you use?
Well, I'm using, if you have a connected affine variety mapping to a projective variety or a complete variety with finite fiber, then then it's so if you don't have connectedness, it's a finite number of points, but now it's connected. So
Why would we be able to assume that DG was something?
say that again.
Why would we assume that DG was actually trivial?
Sorry, why is DG acting trivially?
Why we can assume that?
Because I have produced a new. Oh yes, I always forget. Thanks. So oh, maybe later on we do that. So the question is, why can I assume DGX trivially on V? So here we have produced a new projective variety, and it's non-empty, right? Because DG has a fixed point. So this is a projective variety because it's closed in V. So I can now replace with W. I can just consider G action on W, DGX trivially. If I can produce a fixed point in W, then I produce a fixed point in V, right? Okay. So now let me just say this a corollary of Lee-Cauchy. Well, it's a theorem of Lee-Cauchy, but now we can deduce it from the Borel's fixed point
Ting.
theorem. So if
Ting.
G is a connected solvable, and the closed subgroup of G of N,
Ting.
then there exists some G so that it will conjugate the G into upper triangular matrices. So sorry. So we wanted to apply this Borel's fixed point theorem. So we just need to show that every element in G fix, so G fix a flag. So we can apply the theorem to the G action on the flag variety. Of course, I didn't discuss flag variety, but this is a projective variety. So this is what we wrote down the other day, the set of all flags. and you can give it a projective variety structure. Okay, so I guess I'm out of time, so I'll stop here. Oh, thank you. Yes.
So we should thank Ting. Are there any more questions from here or from Hawaii?
So do we really need to use the flag variety? Can we just use projective space?
Oh, that's a very good comment. So the question is, do we have to use flag variety? Can we use projective space? Yes, you can also induction, perhaps. Also, there's, I suppose there is a more elementary proof of Lee coaching, but yeah, you probably don't need to use Broyle's fixed theorem, and maybe that can be your exercise for this afternoon.
Is the G same as the way function here written in GL? So it's G equals G. So this would be the same. I think the G is the same within GLN.
Oh. Oh, yes, very good, thanks. Yes. Yeah, otherwise my G inverse is equal to G. Yeah, thanks, Martin.
Are there any other questions from Hawaii?
No.
No?
I guess.
Okay,
Okay.
cool. Well, let's thank Ting again.